Welcome again. I'm Tom Irvine, and today we're talking about the Olive View Hospital and its seismic response. So in 1971, the San Fernando earthquake occurred, and it occurred as shown in the center of that image, and it had a magnitude of 6.5, and the shaking lasted about 60 seconds, and tragically there were 65 people who died in that earthquake. And we'll start to talk about the 1971 earthquake. And then close by in Northridge in 1994, there was another major earthquake. So here is the Olive View Hospital and the damage that it suffered in the 1971 earthquake. And this hospital is located in Sylmar, California. It was originally built in 1964, and it was built in compliance with the earthquake codes of that time, but those codes were insufficient. And then the hospital partially collapsed during that earthquake and later had to be demolished, and a replacement hospital was built in its place. So this is some ideal concepts for generic buildings. So we have a floor at the top left image, and those floors function as diaphragms, shear diaphragms. There's cross beams, there's columns, and there can also be shear walls. And then the shear walls and the columns have to bear then the weight load of the building, including all its contents. And then in the event of an earthquake, there is this lateral ground motion will occur, of course there's vertical motion too, but mostly concerned about the ground lateral motion. And then that creates what's called inertial loads then on the different floors and elements of the building. And then there needs to be continuous paths for those loads then to be redirected into the ground. So as the ground shakes, the building's mass elements undergo acceleration, thus developing inertial loads, as we mentioned. And those dynamic loads from those reactive elements must be carried across the floors. And diaphragms to vertical elements in the lateral load systems, and then to the foundation, and finally to the ground. The building must have these continuous load paths from the roof to the foundation for safety reasons. And the load paths for different load actions, key structural elements constituting load paths, the vertical load paths and the lateral load paths. So here shows a column that failed, reinforced concrete column in the Olive View Hospital. And this hospital did have a vertical shear walls in its upper stories to carry the inertial loads. However, the first floor did not have shear walls. Instead, the load was carried by the first story columns down to the foundation. And this discontinuous design was what we call a soft first story, which is a huge issue in buildings, in active seismic zones. And as a result, the columns failed, and there is a parameter we're going to call the drift ratio. So one of the first story columns actually underwent 0.81 meters of lateral displacement and a clear height of ratio, and then convert that into percent. That near story drift is 19%, and that's shown there at the top of the slide. Now, the American Society of Civil Engineering has drift limits that are about 2 to 3%, but 19% was almost 10 times higher than that 2%. Now, these images may not be exactly correct because these columns, they tend to deflect into what's called an S shape, but we'll just go ahead with this anyways. So this is demonstrating inter-story drift comparison where the code is at 2%. And then at the Olive View Hospital, that at least one of these columns had a 19% drift. So again, almost 10 times greater than the 2% limit. Now these columns, these steel reinforced columns, they also need either ties as shown on the left, or spirals as shown on the right. Well, unfortunately, poor workmanship contributed to the building's failure. The first story columns were spirally reinforced as shown in diagram B, but the spirals were not connected to the top, to what's called the spandrel girder. So it was a poor workmanship. And as a result, a plastic joint was created that was unable to provide the needed lateral confinement. So here's some further failures that happened in the Olive View Hospital. And we have then this steel reinforced concrete in this section of this roof area here. That top bar is in tension, and then this bottom bar went into compression, and that compression did cause a buckling failure to happen. So some review here of what we talked about. So we have features. So the first story had a soft story stiffness mismatch. And then the modern solution is continuous shear walls or brace frames. Reinforcement, the premature spiral termination we mentioned. So the modern solution is to do the job right in the first place and have continuous confinement into the joints. And for the load path, then, there was a discontinuous path to the foundation at Olive View Hospital. And what we want are redundant and continuous load paths. Here is the seismic code evolution for the state of California. We're going to mention schools and hospitals. So the big earthquake in California, in fact, the worst case earthquake in U.S. history in terms of loss of life and property damage, was the 1906 San Francisco earthquake. Then the next big one to come along was in 1933 at Long Beach, and that required seismic design for California's schools. So this was the Field Act that came as a result of that earthquake. And it was the first major seismic law in the U.S., again covering schools but not hospitals. And the Olive View Hospital, the original one, was built in 1964, and under the existing codes of the time, which were insufficient. So at that time, there's no hospital-specific design rules. So soft story design and poor column confinement, that left it critically vulnerable, as we've mentioned. Then in 1971, the San Fernando earthquake came along with magnitude 6.5. The hospital partially collapsed, and hospitals are critical to disaster response. Of course, the hospitals have patients receiving ongoing care. They need to remain open to receive the incoming wounded. So there's an acronym here, this OSHPD, that's the Office of Statewide Health Planning and Development of California. And this Alquist Act of 1973 created this oversight. So hospitals must remain operational post-earthquake, advanced soft story designs, and required continuous load paths. In 1987, the new Olive View Hospital opened up, and it was built under these OSHPD standards and continuous shear walls, proper confinement, spread footings. Now, it survived the 1994 Northridge earthquake intact, but there's a bit more to the story. We'll get to that shortly. So here's the image of the new hospital, designed to withstand increased levels of ground motion based on lessons learned. Very strong and stiff. The foundation consists of spread footings and concrete slab on grade for the first floor. I've got an appendix slide that will explain what slab on grade is at the end of the presentation. The first and second stories are built of concrete, and then shear walls 25 centimeters thick. And steel shear walls are used for the remaining upper stories. So in 1994, the Northridge earthquake comes along, occurring at 4:30 a.m. local time, January 17th, 1994. And Northridge is about 30 kilometers northwest of Los Angeles. Now this had a 6.8 magnitude, which is a bit higher than the San Fernando, but yet the duration was shorter, just 10 to 20 seconds for the Northridge quake. And the hypocentral depth was 19 kilometers. So if we talk about the epicenter, that's the point in the ground level above the true earthquake source, and then the true earthquake source is then below at some depth. The earthquake occurred along a blind thrust fault close to the San Andreas Fault. So a blind fault is a buried fault that does not extend to the surface. So the U.S. Geological Survey and the emergency officials did not know that this blind fault was there, but the oil companies did from their oil exploration. But the oil companies kept that information as proprietary, whereas ethically they should have shared that information with the U.S. Geological Survey and other government officials. So these buildings are actually in active seismic zones, are monitored 24/7 with accelerometers. And this is the 1994 Northridge earthquake at the new Olive View Hospital. At ground level, there was 0.9 Gs, but due to some resonant dynamic amplification in the roof at 2.3 Gs. So the building structure's fundamental frequency is estimated at 2.5 hertz in the north-south axis. That's a rocking mode, and we'll talk a little bit more about rocking modes in some upcoming slides. Dominant earthquake excitation at the hospital's foundation was in the 2 to 3 hertz domain, largely a result of the local soil conditions. So we see 2.5 hertz for the natural frequency, and then the dominant excitation was 2 to 3 hertz, so that's set up that dynamic resonant amplification. Now, it wasn't all good news. The good news is the new Olive View Hospital remained intact, but a water pipe broke, and that forced the evacuation. So here are the patients and doctors and nurses caring for the patients out in this parking lot area. So it's also important that the non-structural equipment, piping and so forth, have sufficient bracing inside the hospital or the building, whatever it might be, and we'll talk more about that in future units. So we mentioned the resonant, but the good thing was there's a fairly good amount of damping. So one of the damping mechanisms may have been the radiation damping, whereby the building dissipates energy into the surrounding soil. So damping, we say, controls responsive resonance, and there still was some dynamic amplification, but the damping somewhat mitigated that amplification. So the measured damping for the Northridge event was 10 to 15%, which is a really good amount of damping in the north-south axis, and in the 5 to 10% in the east-west direction. Rocking modes. Here's the natural frequency of a rocking mode. It's 1/2 pi square root. We have a rotational stiffness. Now this rotational stiffness that includes the building, the foundation, and the soil is an elastic soil. All those combined together make up this rotational stiffness. And then I will be the mass moment of inertia about the base. So rocking is a soil structure interaction mode. And you'll see that a little more clearly on the next slide. The foundation flexibility lowers the stiffness system. Radiation damping occurs as rocking energy propagates into the soil. Controlled rocking can increase the effective damping, reduce internal force demand, and limit structural damage. So this is an interesting idea about rocking, is that in New Zealand, for example, there have been some buildings. New Zealand's a very active seismic zone. There are buildings and structures designed to undergo rocking, and you'll see that the reasons for that on the next slide. By the United States, we haven't done this yet with our buildings. Now here is the idea that it's done in New Zealand and maybe a few other countries as well. So on the left, we have what's called a conventional capacity design. This looks like it could be some type of a tower or some kind of column. But anyways, regardless, then we have this vertical section, and we have like a plastic hinge, and there's some cracking going on. So a plastic hinge, practically elastic foundation response, and it's on a larger footing. And then we can have a smaller footing off to the right. And in this case, there's going to be no damage to the superstructure, which is a distinct advantage. But there's going to be a full mobilization of the foundation capacity. So there's going to be rotation and settlement, and this tower building, whatever it might be, may end up like the Leaning Tower of Pisa with some permanent angular displacement. So kind of a good news, bad news, but again, some success with this in New Zealand. A little bit of review here. So yeah, now this says 1971 hospital. It's actually the hospital was built in 1964, but it had to be torn down in 1971 after that big quake at San Fernando. And then we have the new hospital for comparison. So the old hospital had a soft story, the new one did not. The old hospital had poor confinement, and the new hospital has modern design standards and up to workmanship standards. Both underwent resonance. The old hospital collapsed, the new one remains intact. We don't know the damping for the 1971 hospital. That the new hospital, as we mentioned, at least in one axis, was up to 10 to 15% damping. Now here is the final slide, and this is going to be the slab on grade foundation. Now my background is more of a mechanical engineering background, so some of these basic civil engineering things I'm still learning. I do understand the signal processing and the shock and the dynamics. That I feel confident in, but some of these basic things I'm still coming up to speed. So this will be a foundation for a home. It's called slab on grade. There's no crawl space. And a slab on grade is a concrete poured over a layer of approved vapor barrier material that is usually placed on the base of gravel throughout. It's placed directly on the ground or grade level. When the concrete is poured at once, it's called a monolithic slab, and there's no breaks or joints. And then there's going to be wire mesh used to reinforce the concrete. And the concrete's edge is poured to a greater thickness, and reinforcing rods are installed for stronger footing. So a little civil engineering for you there, construction engineering, which you probably already knew about that, but I put that in so I could learn more about this. So thanks for coming today. We'll have more fun next time we come as we continue to talk about earthquake engineering. Have a wonderful day, and bye for now.